An interesting aspect of Prolog is that it was in fact designed for convenient and efficient text processing. Prolog originates from queue systems, which were used to translate weather reports between French and English. And to represent text in Prolog, it's best to use lists of characters, which are also called strings. And strings are an ideal representation of text for several reasons. First, and maybe most importantly, they are very easy to read and write in programs, queries, and answers. Second, they can be partially instantiated with unknown elements. And also, since strings are lists, we can reason about them with existing predicates over lists. So we don't have to teach and learn any additional predicates. And strings are also great from a performance perspective, because they can be very compactly represented in memory, using, for example, UTF-8 encoding internally. And strings are most convenient to use if the Prolog flag double quotes is set to the value chars, because then we can use double quotes to write lists of characters, like this. So this is a list with exactly 3 elements, the atoms A, B, and C. And we can write the string equivalently using list notation. So this succeeds, because the terms are the same. And this is already the default in newer Prolog systems, such as Scryer and Tau Prolog. And in fact, that's also what the original Prolog system, Marseille Prolog, did, because it was intended to make string processing as convenient as possible. And as mentioned, we can use existing list predicates to reason about strings. For instance, if we want to parse a sentence like this, then we could use, for example, the well-known predicate append to state the string we want to parse starts with hello, followed by characters ls1. And as answer, we get the characters ls1 that come after hello. Now, we can of course generalize this and say the string we want to parse starts with a greeting. It could be hello or also some other greeting. And we say that the greeting is followed by a space. So for example, in this case, the string is parsed in the sense that we have found the greeting, hello in this case. And on backtracking, we also get other solutions, such as hello world for the greeting, and also hello world and no other solutions. Now, we can, for example, constrain the greeting by stating greeting is, in addition to being followed by a space, something for which the predicate greeting holds. And we can use this predicate to define, for example, that the string hello is a greeting. And if we're interested in what is being greeted, we could again use append to look at the next word or words followed by a space. So yes, we could use append and other predicates over lists to reason about strings. However, I think it's clear from such examples that this wouldn't be very convenient, right? So what we'd like is a better formalism to reason about lists and strings in particular as a specific kind of lists. And I say reasoning because we want to generate, parse, complete, and test lists. That is, we want to use logic programs to their full potential as executable specifications that work in all usage modes. And finding such a formalism is not easy. In fact, it took the inventors of Prolog years to find it. But now it's here. Virtually all Prolog systems ship with a built-in grammar mechanism, definite clause grammars, DCGs. A DCG is defined by a sequence of grammar rules. And these rules define non-terminals. And a grammar rule has the form grammar rule head, gr head, then an arrow from left to right, and then a grammar rule body, gr body. So that's the syntax of a DCG rule. And the meaning, that is the semantics of a non-terminal, is that it describes a sequence. The rules of the same non-terminal denote logical alternatives, similar to clauses of a predicate. And each grammar rule body consists of terminals, non-terminals, and grammar body goals. A terminal is written as a Prolog list and stands for the elements it contains. A non-terminal is written like a Prolog goal, except that it refers to a DCG non-terminal instead of a predicate. And it stands for the elements that the non-terminal describes. And we use f/n to refer to the non-terminal f with n arguments. So we use double slash instead of a single slash to distinguish a non-terminal indicator from a predicate indicator. And a few non-terminals are already predefined. The most important ones are comma with 2 arguments. This means concatenation, and we read it as and then. So that's different from comma in predicates, which we read as and, that is conjunction. and vertical bar with 2 arguments, denoting alternatives, and we read it as or. And the predicate phrase holds for GR body and LS if and only if LS is a list described by GR body. So we can think of this predicate as it holds for the sequences described by a grammar rule body where the sequences are manifested as Prolog lists. So these are the most important points about DCGs. And we conclude with a few examples. For instance, let's describe lists that consist of any number of A's, okay? And we do this by defining a DCG non-terminal, let's call it A's, that describes exactly such sequences. So we say the non-terminal A's describes, and now we consider possible cases, for example, the empty sequence. Or, so as an alternative, a sequence consisting only of the character A. Or a sequence of 2 A's. And as mentioned, we can write strings equivalently using double quotes. So we can write these rules more compactly. And for consistency, we can also denote the empty list with double quotes. So what else do we want to describe with this non-terminal? Certainly a sequence of 3 A's. And in general, any sequence that starts with an A and then a sequence of A's, right? And in fact, this last rule subsumes all these special cases. So we can delete them. Because we only need these 2 grammar rules, where we've used the terminal nil, the non-terminal comma, which we read as and then or as followed by, the terminal A, that is a list with a single element, the atom A, and the non-terminal A's, which we're also defining, and which we define to mean a sequence of A's. And we can read this DCG informally as the empty sequence is such a sequence. And so is a sequence with first element A and then A's. So this example DCG is very convenient to read and write and also easy to understand. We describe sequences and we can read the definition by considering the alternatives. Now, how do we use this grammar? Well, DCGs aren't yet part of the Prolog ISO standard. However, they are currently being considered for inclusion in the standard and a draft is already available. And as mentioned, almost all Prolog systems already support DCGs, even though a few details vary between systems. For instance, in Scryer Prolog, we import the DCGs library. So we add to our code a directive that imports library DCGs, okay? And since DCGs are very often needed in Prolog programs, I recommend to add this directive to your Scryer C configuration file so that you can use DCGs in all programs without having to add the directive. And phrase, which we mentioned, is the main interface predicate for using DCGs. And DCGs blend in seamlessly into Prolog, and they also exhibit a characteristic that is typical for Prolog code, namely the same code can be used in different directions or modes. For instance, we can ask, using phrase, about sequences described by the non-terminal A's manifested as a list ls. So that's what we call the most general query for this non-terminal, because we ask here, are there any solutions whatsoever? And we place no other constraints on ls. And as answer, we get a concrete solution. The empty list is such a list. And on backtracking, we get alternatives. So all these lists are solutions, because they are such sequences consisting only of A's. So we see that we can use this definition to generate such lists. And we can do more. For instance, instead of using a free variable ls here, we can state a more concrete term, such as, say, this list where a few elements are not known. And as answer, we get again a concrete solution. This says the list is a solution if x is a and y is a. And that's the only solution. So we can use the same definition to complete lists, in the sense that now everything is known about the list, whereas in the query, 2 elements were not known. And we can make the query even more specific by asking, does this fully known list manifest such a sequence? And Prolog answers, no, that's not what the non-terminal describes. So we can use the same definition to test whether a concrete list is a solution. And we can, of course, write concrete strings more compactly by using double quotes. And for example, this string is a solution, because the predicate succeeds unconditionally. So we've seen that we can use the same definition to generate, complete, and test solutions. And this generality is one of the reasons why Prolog and DCGs in particular are hard to teach. Because if we want to convey the full generality of such definitions, then we must choose our words carefully. For instance, if we say the rule generates a list or the rule consumes a list, then we only capture specific usage modes, even though the same rule can be used in other modes too. And we therefore say, for example, the grammar describes a sequence in order to subsume all possible usage modes. And a good naming convention for non-terminals is to reflect what they are describing. So when choosing a name, we ask, which sequences are we describing? And if they have a telling name, then that's a good choice. And this naming convention for non-terminals is different from the one we use for Prolog predicates, where we try to find good names for the arguments of the predicate. So here, we are focusing on the sequence we are describing. And even though the naming conventions are different, grammar rules are very strongly related to Prolog rules. In fact, every DCG non-terminal can be easily converted to a Prolog predicate. For instance, in our specific case of the non-terminal A's, we can define a Prolog rule A's which holds for ls0 and ls if ls0 and ls are the same. And alternatively, it holds for ls0 and ls if ls0 is a list that starts with the atom A and the tail is ls1 and A's holds for ls1 and ls. So we see that we can mechanically translate a grammar rule to a Prolog predicate using list differences to make concatenation efficient. And this is in fact how most, if not all, Prolog implementations provide DCGs, by a straightforward term expansion that translates grammar rules to normal predicates. However, this expansion is implementation dependent and may also change depending, for example, on the phase of the moon or on other factors. So, as Prolog application programmers, we must not rely on a particular expansion method. For example, in some Prolog systems, such code may be more efficient if the arguments are exchanged like this. And this may lead to fewer virtual machine instructions and so on, depending on the system's architecture. And therefore, as application programmers, we always use the DCG interface predicates, such as phrase, to invoke a DCG. Because this keeps our code portable between implementations, no matter how they implement DCGs internally, okay? As another example, let's consider this challenge by Tim Sweeney. Can we write a function print xy taking an integer n greater than or equal to 0 that prints all strings of length n containing only the characters x and y? So no, we can't write a function because we are thinking here in terms of relations, and we don't just print something because we want to reason about the strings we describe. However, we can still do something. For instance, we can define a non-terminal xy and say which sequences we mean with it. First, the empty sequence is such a sequence. And as an alternative, any sequence that starts with the character x or the character y followed by any sequence described by the non-terminal xy is such a sequence, okay? And now we can use this declarative description in many ways. We can ask, for example, the most general query. What do solutions look like in general? And as answers, we get sequences that the non-terminal describes, manifested as strings. And we note here that we only get x's. This is called an unfair enumeration, because there are solutions that we'll never observe in this enumeration. And one way to get a fair enumeration is to limit the length of the list before we invoke phrase, because in this way we get all solutions for the given length. This yields a search strategy called iterative deepening, because we first get all solutions for length 0, there's only one such solution, the empty list, then all solutions for length 1, there are 2 of them, then all solutions for list of length 2, then all solutions for a list of length 3, and so on. So we get longer and longer lists, and for each length we get all solutions. And we can of course also ask for a concrete given length, say 3. So now we ask, are there any solutions for a list of length 3? And yes, triple X, and also several other solutions, for 8 solutions in total. And instead of 3, we can of course also ask for lists of any other length. So we are in no way limited to small lengths. And as before, this definition can be used to generate such strings and also to complete and test them. And as mentioned, it works for every length n. And the length n can be specified and also generated using, for example, the predicate length as we've done. So this is a relation which can be used in all directions. That's much more versatile than just printing. So this is an example where DCGs come in handy. And many tasks can be nicely expressed with this mechanism, especially when reasoning about lists. And a few basic building blocks often come in handy. And as one such building block, let's introduce sec, which we want to describe the list in its argument. So we say sec of the empty list describes the empty sequence. And sec of a list with at least one element L and tail ls describes a sequence that starts with L and then the sequence described by sec of ls, okay? So that's an executable specification and we can again use it in different modes. For instance, what is the sequence described in this case manifested as the list ls? It's of course the given string abc. And in this case, it's the concatenation of the two strings, which we can also test if we specify the expected result in the query, which succeeds. And we can generalize this by using variables in the arguments, and then we get these decompositions of the string as solutions. So this is a very general relation, and if we wanted to, then we could define the well-known predicate append in terms of this non-terminal. Because this holds if zs is the concatenation of the lists x's and y's. And we can easily generalize this to the concatenation of any number of lists, not just 2. And a good name for such a non-terminal is not this, but rather sec_q. So if there are no lists, then it describes the empty sequence. And if there's at least one list ls and possibly remaining lists lss, then it describes the sequence starting with the elements of the list ls, followed by the concatenation of the lists lss, right? And we can use it, for example, if we have such nested lists like this, where we remove one level of nesting, obtaining the concatenation of all these strings. As another example, let's define QES, the reverse of sec, to describe the list in its argument in reverse. So the reversal of the empty list is the empty sequence. And the reversal of a list with at least one element L and tail ls is the reversal of ls followed by L. And with this definition, we can, for example, define what we mean with a palindrome. So let's define a relation palindrome which shall be true if and only if its argument is a palindrome, which is a string that is the same as its reverse version. So we say palindrome holds for the list ls if ls is the same as its reversal, QAS of ls. And we can post the most general query, are there any palindromes? Yes, of course. And what about this concrete string? It's not a palindrome. But for example, this is a palindrome. And this partial list can be completed to a palindrome. In fact, to infinitely many palindromes. So again, we have an example where the same code can be used to test, generate, and complete lists. Another useful building block, and one of the most versatile, is ... without any arguments. We use this to describe any sequence at all. And we define it as either the empty sequence or a sequence starting with any element followed by ... that is any sequence at all. And that's it. And as so often, we start with the most general query, asking for any solutions at all. The empty list is a solution. And so is any list with exactly one element and two elements, three elements, and so on. So really every list is a solution. In particular, this one. And this non-terminal is really versatile. For example, we can use it to express the last element of a list. For instance, in this example, the atom C is the last element in the string, and there is no other last element. And more concretely, as a test, is B the last element? Or more generally, does B occur anywhere in the string? Yes, it occurs exactly once. And if we remove B, then this query fails. So we can use this to detect whether a character or a substring occurs in a string, like grep. And we can also generalize this and ask for lists ls that have B as an element. So in this case, the Prolog system generates such lists. All these lists have B as an element. In fact, all these lists have B as the first element. So that's again an unfair enumeration, because there are solutions that will never be generated. And we already know how we can obtain a fair enumeration by using, for example, the predicate length to fix the length of the list, like before. And now we get all lists that contain B enumerated in a fair way using iterative deepening. So now we get B occurring also as the second and third element and so on. And we can generalize this from B to any element X. Now, this in itself may not seem very useful. It's the common list predicate member. But what about this? We now describe lists that have two successive identical elements. And more concretely, instead of ls, we can ask, are there any two successive identical elements in this concrete string? And in this case, we no longer need the length goal. And as answer, we get yes, L, O, and exclamation mark each occur twice in a row, and no other characters do. And due to this versatility, we again say that we describe such lists, because we can generate, test, and complete them. So from these examples, we see that ... is a very versatile and useful non-terminal, which may be a bit surprising because it seems so simple and unimportant at first. And for example, in Scryer Prolog, sec, seq, and ... are provided in library DCGs, so we don't have to manually define these building blocks. DCGs are also frequently used to relate trees to lists. For instance, let's describe the nodes of a binary tree, where we assume that the tree is either the atom nil for the empty tree, or a term with principal functor node with 3 arguments, the name of the node and the left and right subtree, where left and right are binary trees of this shape. And if we have such a tree, then we can, for example, express the in-order sequence of nodes with a DCG. Let's define a non-terminal nodes, because that's what we want to describe, a sequence of nodes, where we say the empty tree, nil, has no nodes, so that's the empty sequence. And second, a tree of this form yields the following sequence of nodes. First, the nodes of the left subtree, then the name of this node, and then the nodes of the right subtree. And now we can ask, for example, what are the nodes of, say, this tree? And written like this, it's not really a binary tree, because the compound terms have 3 arguments. But it's clear what we represent with this term, right? Namely this tree, so that's a binary tree. And we're interested in the in-order sequence of the nodes ns, which is ACB in this case. And a nice feature of this solution is that we can so easily obtain different orders simply by moving grammar elements in the body. For instance, if we move this terminal to the front, then we get the pre-order sequence of nodes, and so on. So that's nice. Now, you may of course ask, is describing the nodes of a binary tree ever really needed? Or is it just one of these purely theoretical problems? Can I get a job by describing the nodes of a binary tree, and so on? So I change 4 words here. Let's describe the tags of an HTML document. And let's fetch the document from a website using Scryer Prolog's HTTP Open library by Adrián Arroyo. And also we use library SGML to represent the document as a tree. So we open a connection to, say, my homepage, obtaining a stream S using the default options, and we use that stream to load an HTML document represented as a document object model, a DOM, again with the default options. And as answer, we get such a nested term. And we want to extract the tags that occur in the document. So we are, at least for this task, not interested in the structure of the document. We only want the flat list of tags. So for instance, we want HTML, head, and so on. Now, in this representation, each HTML element is either a string or a term of the form element of tag name, attributes, and children. And for our task, we can ignore the attributes. The important thing in our case is the tag name, in the element and also in its children. And I leave it as a challenge to define a non-terminal tags that relates such elements to a sequence of tags. And once we have such a non-terminal, we can ask for the tags that occur in the DOM, manifested as a list T's. So this is another example of what I mean with relating trees to lists. Because in this case, we have a tree, the HTML document, and we relate it to such a list of tags. It's clear, right? But on the other hand, wait a minute, because isn't a list, in a sense, also a tree? Yes, of course, right? Because such a list is also a Prolog term, and terms have a natural representation as trees. So, in a sense, we are always relating trees to trees. It's just that sometimes we want to remove structure, as in this case, where we are only interested in a flat list, regardless of how the tags are nested, and sometimes we want to obtain structure. For instance, we may as well have the converse case, where we have a flat list of characters and want to generate such a document object model. And in fact, this task also arises here, and load HTML solves it for us. And this brings us to parsing. Parsing is also called syntactic analysis or syntax analysis, and it means the analysis of input into component parts. In fact, the word stems from parse, which is the Latin word for part. And very often it means that a list of characters or tokens is given, and we want to relate this list to an abstract syntax tree, an AST. So it's a relation between syntax trees and lists of characters or tokens. And therefore, again, a relation between trees and lists. This means that parsing occurs as a specific usage mode of DCGs, namely a case where the list of characters or tokens is known. And even though DCGs come in handy for this task, it's in fact preferable to avoid parsing when possible. We can do this by writing syntax trees directly in our programs and queries. For instance, instead of the string 1 + 1 + 1, we can use a compound term with principal functor plus. And we can also absorb Prolog's parser, for example with read from chars from library chars.io in Scryer Prolog. But sometimes we need to parse input manually, so to say, namely in cases where the structure we want to reason about is implicit in the input and we want to make it explicit, so that we can reason more elegantly and more efficiently about input. And as an example, let's parse simple arithmetic expressions of the form 1, 1 + 1, 1 + 1 + 1, and so on. But in fact, let's not even think about parsing. Instead, let's do what we always do. Let's describe such expressions, okay? So, what do such expressions look like? Certainly, the string 1 is one expression. And also, any such expression followed by the character plus and then an expression is also such an expression. So, let's try the most general query. Can we generate these expressions? Yes. And can we test expressions? For example, is this one of the expressions we want to describe? When we post it, we get non-termination. And what about this one? Yes, it's such an expression, and on backtracking, we again get non-termination. So, if we add false here to focus on just the universal termination property, we see that the query doesn't terminate. Now, why doesn't it terminate? And I'm not interested in the exact steps that the Prolog system performs. Rather, I'm interested in an explanation, a reason for it. And we get such reasons in the form of program fragments by selective reading. And we do this by inserting grammar body goals in the definition. A grammar body goal is written in curly brackets like this. So a goal in curly brackets means that a normal Prolog goal is called at this position. And in this way, we can refer to Prolog predicates from within DCGs. And in particular, if we insert false, then we obtain failure slices. Because false is always false, everything that follows has no influence on termination. And we denote with strikeout text those parts of a program fragment that have no influence on termination. And we can insert false anywhere we want. For instance, in our definition, let's insert it here. This means that we can ignore the first rule entirely. Because with this added false, it has no influence on termination. And further, let's add false, for example, here. This means that we can ignore everything that follows. And with this fragment, we still get non-termination. And now we see a reason for the non-termination, because just this fragment by itself already causes non-termination. And this is called left recursion, because we recursively refer to a non-terminal before any terminal. And there are of course ways to make it terminate. For example, we can use a different execution strategy, such as SLG resolution, also called tabling. So for example, in Scryer Prolog, we simply add a directive to load the tabling library, and we add another directive to enable tabling for the non-terminal. So this is maybe the easiest way to make the query terminate. We simply change the execution strategy. And that's of course possible because our program is an executable specification and we make no assumptions about the execution strategy. And indeed, the query now terminates. And combining DCGs with tabling yields what is called packret parsing. And there's a nice paper by Beckett and Chomodier about it, with various performance considerations. Another thing we can do is, of course, to eliminate the left recursion. This is a well-known technique from compiler construction. In this case, we simply eliminate the rule with the left recursion and state this a bit differently by introducing X per R. R for remainder or rest. And this rest is either the empty sequence or plus and then another expression. So stated like this, the query terminates. And yet another way to make the query terminate is to retain the original left recursive formulation and to take into account the number of required terminals earlier. So what I mean is we add arguments to these rules where we represent as a list difference the number of characters or tokens that need to be present so that the rule can apply at all. For instance, this first rule can only apply if at least one character is present, because the rule only applies if the digit 1 occurs in the sequence. So we add here a list difference that expresses this. This rule only applies if one element is present. And the second rule also needs at least one element present for the plus. And the relation between rs0 and rs is a list difference between rs0 and rs1 and rs1 and rs. So what we've achieved now is that the necessity for the presence of one terminal, this plus here, is stated earlier, namely already in the argument of the rule. So this rule can only apply if at least one character is present. Operationally, we can also think of this as expressing that when parsing, the rule consumes one terminal, and it can only apply when at least one terminal is left. And we use the list we want to parse, let's call it Cs. So we use Cs not only as the input, but also to keep track of the number of characters that are still left. And we don't even care about the eventually remaining characters, even though we know that it's the empty list. And now the query terminates. So this is maybe the most elegant approach to solve this, because it lets us retain the original left recursive grammar, which is natural to read and write, and at the same time, it also works in all Prolog systems and with all execution strategies. Of course, there's now some overhead because we now use additional arguments, but the other ways to solve it also come with their own downsides. They require changes in the grammar or work only if the Prolog system provides, for example, SLG resolution. So now we've described such expressions as strings. Let's now actually parse them as we originally intended. Parsing usually means that we relate lists of characters to syntax trees. So all we have to do here is to write down the syntax tree corresponding to each expression. For instance, in the first rule, when we encounter a 1 as a string, then we simply use the integer 1 to denote this expression. And in the second rule, let's denote this addition, which we encounter here as a string, as a compound term a plus b, where the arguments a and b are the syntax tree of the sub-expressions that occur in the string. And in the query, we simply ask for the parsed expression e. And as answer, we get this as the first solution, this as the second solution, and no other solution. So what we see here is that this string can in fact be parsed in two different ways. It can be parsed as the expression 1 plus 1, associating to the right, and also as 1 plus 1 plus 1, associating to the left. So the grammar is in fact ambiguous. So this is what we mean by parsing, relating a list of characters to syntax trees. Or rather, as mentioned, characters or tokens. What is a token? Well, this brings us to lexical analysis, which is also called Lexing and tokenization. And it's a relation between a string and a sequence of tokens. And with a token, we mean common syntactic categories, such as a keyword, a literal, a constant, a comment, an identifier, and so on. And we say we tokenize a string by finding demarcations between its tokens. For instance, let's relate a string to the list of its words. So we start by defining a non-terminal that states what we mean with a word. And let's say we accept the empty word and also a sequence of a character C on the condition that C is an alphabetic character. So we use char type from library chars.io to state this constraint. C must be an alphabetic character. And we use curly brackets because this refers to a Prolog predicate, not a non-terminal. And then a sequence that satisfies our definition of a word. So in other words, a word is a sequence of alphabetic characters. And we can define a sequence of words separated by whitespace and possibly also surrounded by whitespace as another non-terminal, say word z, which is either the empty sequence or whitespace, then a word, then again whitespace, and then a sequence of words, where we define whitespace as either the empty sequence or a whitespace character. So char type comes in handy again to state W must have type whitespace followed by whitespace. And when we now ask, is it the case that this string is a sequence of words which are separated by whitespace, then we get non-termination. Why? Well, we can again use selective reading to generate explanations, and I leave this as a challenge. For now, let's implement what the Prolog standard calls the eager consumer rule. This means that each token shall extend to its maximal length. And we get this by prioritizing rules that extend tokens, by consuming more characters. For instance, for word, we simply exchange the two rules, because now the rule that, procedurally speaking, extends a word comes first. And the same here for whitespace. We slightly rewrite this again so that the rule that extends whitespace by consuming a character comes first. And with Prolog's default execution strategy, this will also be tried first. And with these slightly changed definitions, when we now try the query from before again, we get success and possibly other solutions. Now, what we actually want is the list of words, and to get them, we equip the rules with arguments so that we can refer to the described words. So we define the word that is described by this rule is a list of characters starting with C and tail Cs, where Cs are the characters in the remainder. And the empty sequence corresponds to the empty string. And the empty sequence of words corresponds to the empty list. And otherwise, we have a list starting with W if we encounter the word W, and tail Ws for the following words. And now we can ask for Ws, the list of words in the string, and we get them, and also other solutions. And of course, we expect this to terminate, right? But it turns out that it unfortunately doesn't. But we can still use this definition because it turns out that the first solution we got was exactly what we intended, namely the list of words. And we can use once to obtain only the first solution. So we simply wrap this goal in the standard predicate once. And then we get exactly one solution, namely the first one. And the goal terminates. And it also works, for example, if more whitespace appears in the string, like this. We again get the list of words. And this example also illustrates why we call an abstract syntax tree abstract, because it ignores syntax elements such as whitespace, punctuation, comments, and so on. And such elements are part of the concrete syntax of a language, and they can be safely ignored in many cases. And as another example, let's describe an integer in a string. So we say an integer, let's call it I, occurs in a sequence if there are digits ds, a list of characters, such that I is the integer represented by the digits ds. And there are digits, first digit d and remaining digits ds, in a sequence if the sequence starts with the digit d followed by remaining digits ds. And the remaining digits are either a digit d followed by further digits ds, or no digits at all. That is the empty sequence. And we like to align the rules like this. And a digit d occurs in a sequence if there's a terminal d such that d is a character and the type of the character is, say, decimal digit. Okay? So for example, is there an integer I that occurs in this string? Well, yes, there is an integer here, but not only an integer, because it's surrounded by whitespace, and therefore the query fails. And therefore, if we ask, for example, is there an integer here that's surrounded by whitespace, then it succeeds, yielding I as an integer. And there are no other solutions. So this is again typical for a tokenization task. We started with a list of characters, which is a tree, where the information we want to reason about is represented somewhat implicitly. And we have extracted a token, in this case an integer, which we can reason about with arithmetic constraints and so on. So we have tokenized the input. And in fact, one could just as well say that we have parsed the input. And indeed, many of us would likely say this. We are parsing the input, right? So what is actually the difference between lexing and parsing? And is there a difference at all? Well, one way to view the situation is to say lexing occurs as a subtask of parsing. So one could say our overall goal is to relate the concrete syntax, which has whitespace, comments, and so on, to an abstract syntax tree. And as one step to obtain this, we tokenize the input and then reason about the tokens. But it's really up to us how we organize the tasks, and it also depends on the language we want to parse. For example, the language we want to parse may have features that prevent a separation of these tasks, because it may make it possible to dynamically change what the token of the language even means. And especially in such cases, we can combine the tasks by handling lexical aspects also in the parser. This yields what one calls a scannerless parser, also a lexerless parser. For instance, we may define what an assignment is in a language by saying an assignment is a relation between a variable and, say, an integer and it may be preceded by whitespace, then a variable, say a word, then whitespace again, then an operator denoting assignment, like in R, whitespace again, then an integer, and possibly ending with whitespace. So whitespace may occur at various positions in such a statement, and it's obviously a bit inconvenient to have to take this into account in a grammar rule at so many places. But we can of course do it like this. If we want to, we can handle all these concrete syntax elements in the parser. And here's a sample query. And as mentioned, another approach is to separate the tasks more strictly by making the lexer generate a list of tokens which the parser uses as input. Well, that's a very procedural view, and ideally we describe a list of tokens. And the parser not only uses them as input, but reasons about these tokens. It may as well generate them from an abstract syntax tree. And with such a separation, we may say, for example, an assignment is a sequence of tokens, such as an identifier, an operator, and an integer I. So the parser now no longer reasons about the concrete syntax, but rather about these tokens. And such a separation is of course attractive for several reasons, maybe most notably because the phases are easier to understand in isolation. And it may also be more efficient and easier to optimize and so on. And whether or not we separate the phases, one of the most interesting aspects is that we need only a single formalism, only DCGs, for both lexing and parsing. So in a sense, we are always scannerless, because we are not using a dedicated mechanism for lexing. We use the same formalism for lexing and for parsing. And that's another way to look at it, to say we have a lexer when we are using a dedicated mechanism for lexing. Yet another way to look at it is to make a distinction based on the expressive power we need for a task. And one possible and somewhat common distinction is to say a parser is something that needs at least a context-free grammar, and a lexer is something that can be expressed with regular expressions. And from what we've now already seen, we know that DCGs certainly let us express context-free grammars, and even context-sensitive grammars, because we can use arguments to reason about the context. And therefore, DCGs also let us express strings described by regular expressions. And of course, we want a nice way to write regular expressions. So let's implement an interpreter for regular expressions. For instance, let's use the empty list to denote the empty sequence. And let's denote with a literal string, a list of characters, the sequence of these characters. Then let's use star of R to denote the Kleene star. So star of R shall mean either the empty sequence, where we don't need to take R into account at all, or it means that the sequence described by R occurs at least once, and then occurs 0 or more times again. So in other words, star of R means R occurs arbitrarily often. Then let's denote with A plus B the concatenation of the sequences described by A and B. And finally, we use a vertical bar to denote alternatives. So that's either the sequence described by A or the sequence described by B. And as before, we prefer a nice alignment of these rules, using a regular expression to align our regular expression code. So let's align at the arrows. And that's it. This is a DCG-based interpreter for regular expressions. And we can use it in several directions. For example, we can ask, given a regular expression like this, what are the strings ls it describes? In this case, it describes arbitrarily many a's, like our initial DCG example. And what about this example, where we use alternation? We again get only a's. So that's an unfair enumeration, and we've seen how we can fairly enumerate solutions by restricting the length of the list beforehand. So that's like our XY example we've seen, except that we now use A and B. And we can also use the same definition to test whether a regular expression matches a given string, like this. And then we no longer need length, of course. So in this case, yes, this is a string described by the regular expression. And we can also ask which regular expressions are describe the string. And we get a solution, admittedly a very trivial one, and then non-termination. But it's still interesting that we have this flexibility at all. And the interpreter can be interpreted also with other execution strategies and may then find also other solutions. And such a situation is in fact quite common. Many interesting programs can be regarded as interpreters. And especially with DCGs, we can easily relate complex data structures to strings, as in this case, where we relate regular expressions to strings. Another interesting example of this, and a bit similar to this one, is relating protein folding structures to amino acid sequences. And again, DCGs are very useful to describe such relations and also to experiment with such specifications using interactive queries and so on. And of course, longer sequences, such as DNA sequences, are usually not entered on the top level, but rather stored in files. So it would be useful to easily process data that's stored in files. And a major attraction of DCGs is in fact that we can transparently apply them to file contents using library PO for pure input and output. This library provides phrase from file with 2 and 3 arguments, which is similar to phrase, except that it applies a non-terminal to the contents of a file instead of to a list. For instance, let's read the entire file contents to a string. For example, let's take test.txt with this sample content. And to read the content to a string, we first import library PO. It already ships with Scryer Prolog, and there are also versions for other systems. And then we say phrase from file of sec of Cs. That is, we're interested in the list of characters Cs, and the second argument is a file name, such as our test.txt. And as answer, we get the string Cs, which is exactly the content of our file. And there's no other solution. Or as another example, we can implement a simple instance of grep. Does the string hello occur in the file? Yes, it does. Possibly more than once even. So a major attraction of library PO is that it allows us to decouple the declarative description, such as what a sequence is, from actual input-output, such as reading a character from a file. This happens completely implicitly by the library. And we, as application programmers, can focus on declarative descriptions. And we can also test our definitions interactively on the top level, even without any file. And on top of this, phrase from file can be implemented very efficiently, for example, by mapping the file directly to memory, using operating system facilities. And this makes DCGs suitable also for analyzing very large amounts of data. So this is for input. And for output, we have correspondingly phrase to file and phrase to stream. And also non-terminals from library format, which are useful for describing output, namely format underscore and portrait clause underscore. For instance, we can use a format string to describe the shape of our output using control sequences to plug in terms from arguments, yielding a list of characters. And with phrase to stream, we can efficiently write the described string to a stream. And library format is available in Scryer, Tau, and Trailer Prolog, and I hope also in more systems in the future. And especially when reasoning about larger amounts of text, it's of course useful to know the exact location of syntax errors. For instance, let's again consider our definition of word, words, and whitespace. And let's try to tokenize a string where these definitions don't work. Why don't they work? Well, because there's a comma in the input. And we get non-termination. Why? Well, we use selective reading to find a reason for the non-termination. For instance, let's insert false here, here, and also here. And even with just this fragment, we still get non-termination. So this rule by itself already causes non-termination, and no change in the strikeout parts can prevent it. And one reason for this is that, as mentioned, we've allowed a word to be empty, right? And we can change this by requiring that a word have at least one character, as we did when parsing numbers, where we required at least one digit. So we introduce a terminal word R for the possibly empty remainder of a word. And with these changes, the query terminates and fails due to the comma in the string. So that's one way to improve this. But let's return to the original definition and let's relate the string to the encountered syntax errors. So we want to turn this into a relation between a string, a list of words, and syntax errors, if any. And let's use a list difference between is0 and is to describe the list of errors. So we equip each of these rules with two additional arguments, is0 and is. And for a start, we simply thread through these arguments, like this. And if there can't be any errors in a rule, then the arguments are simply the same. So the difference is the empty list for no errors, like here. And here, we again thread these arguments like this and this, okay? And now, let's describe a case of a syntax error. For example, let's describe a word consisting of characters Cs, even if we encounter an unexpected character C and possibly also other syntax errors in a sequence that starts with C, where C is not an alphabetic character, because then it would be part of the word, and also not a whitespace character, because then it would delimitate the word. And then a word consisting of Cs and possibly further syntax errors, okay? So we've now augmented the grammar to take syntax errors into account. And when we ask, is this a list of words with syntax errors is, then we get yes, that's a list of words, and the string also contains an unexpected comma. Now, where exactly was the comma? Well, we can also add a position difference between P0 and P that lets us track the number of described characters for each rule. And we can use it to indicate the position at which a syntax error occurs. So we add P0 and P and say P1 is P0 plus 1, because we're encountering one character here, and I leave the rest as a challenge, and analogously for this rule. And now that we know the position, we can refer to it when denoting the error. And say, for example, the unexpected character C occurs at position P0. And in some rules, the position stays the same. So this is how we can also reason about syntax errors, by describing the error and the position. And there's a predicate called phrase with 3 arguments, which can also help us to reason about failed parsing. This is a generalization of phrase with 2 arguments, and it lets us reason about remaining terminals. And it relates a grammar rule body to a list difference. And it's very closely related to the phrase we already know. If we write phrase of grammar rule body S0 and third argument S, then this is almost equivalent to saying that phrase holds for GR body and the list ls, and appending ls and s yields S0. So this means that GR body describes the list difference between S0 and S. And I say almost equivalent because this only holds if there's no semi-context involved, which we'll discuss in a moment. For now, let's consider an example. Let's take a DCG, say our definition of integer and related non-terminals, okay? Then, when we use it for parsing with phrase with 2 arguments and ask, is a given list an integer, such as a list that starts with 1, 2, 3, 4, followed by ABC, then no, that's not an integer, because ABC aren't digits. And we said that an integer consists of digits. But if you use phrase with 3 arguments and ask, does this list start with an integer, followed by a remainder, rs? Then yes, 1, 2, 3, 4 can be parsed as an integer, and the remainder is ABC. And in fact, there are also other solutions. For example, 1, 2, 3 is also an integer, and the remainder is 4ABC. Or this one, 1 and 2 and the remainder. And the last solution, where only 1 is taken as the integer and the rest is the remainder. So in this way, we can see the remaining terminals in a string parsed up to this point. And this can be useful when reasoning about parsers and errors. And one equivalence that always holds is that we can define phrase with 2 arguments in terms of phrase with 3 arguments, where we use the empty list as the 3rd argument to say nothing remains. That is, the entire list ls is described by a GR body. So this version of phrase lets us reason from the Prolog side, so to say, about sequences described by a grammar rule body manifested as list differences. And somewhat related to this is the non-terminal call. This lets us call from within DCGs a Prolog predicate. And that predicate gets passed 2 additional arguments forming a list difference. So it's the flip side, so to say, of phrase, because it allows portable access to the list difference from within DCGs. And we can use this, for example, to express format underscore by calling format within a DCG. So we say format underscore of a format string fs and arguments describes a sequence, and we describe this sequence by calling an auxiliary predicate, say format underscore underscore, to which we simply pass the format string and the arguments. And that auxiliary predicate gets, of course, these 2 arguments and also gets passed, due to call, 2 additional arguments, cs0 and cs, forming a list difference. And this is a completely normal Prolog predicate, not a DCG, where we can, for example, invoke format, if the Prolog system supports it, and say we want to obtain the output as a list difference, the list of characters cs0 minus cs, for the given format string and arguments. So that's how a Prolog implementer can portably provide format underscore by using call. And another example is to express end of string. For instance, we can define end of string is encountered if calling eos underscore succeeds. And eos underscore is a predicate that holds only for the empty list. So not just as a list difference, but as the actual empty list. And due to the way phrase works, we usually don't need to express end of string, because phrase only succeeds if nothing remains. So we usually don't have to say that explicitly. But if we need to express it, then we can do so with call. Another DCG language construct is semicontext notation. And with this, we can denote the presence of remaining terminals in the sequence. Operationally, we can think of these elements as being inserted into the sequence. For instance, to denote that T1, T2 and so on are remaining terminals in the sequence, we write a non-terminal nt, comma, then these elements, T1, T2 and so on, written as a list, and then, as usual, a grammar rule body. So that's a specific form of a grammar rule head, where instead of only a non-terminal, we also have a semi-context. For example, let's define a lookahead of one element. Declaratively, this means that we describe that a specific element is present in the sequence and also remains in the sequence. And operationally, we can think of it as we consume one element and then insert it again. So we define lookahead holds for an element x if x is present in the sequence. So we use the terminal x. However, we want to retain x in the sequence. And so we use semi-context notation to state x is a remaining terminal in the sequence after the application of this rule. And that's it. And when we ask, for example, what is L if we look ahead one terminal in this string, then it fails. That's clear, right? Because phrase only holds if the entire list is described. So we need phrase with 3 arguments here. And now we see L is the atom H, because that's the first character of the string. And the entire string remains as RS. And therefore we could, for example, apply further grammar rules that also see the entire string. So semi-context notation lets us implement lookahead. We can peek into a sequence and retain the element. Another interesting application of semi-context notation is that it lets us pass arguments implicitly. And that's very useful because Prolog programs often describe a sequence of state transitions, where we start with an initial state S0 related to the next state S1, then S2 and so on, up to a final state S. For example, let's count the number of tags in an HTML document. And if you remember, with Scryer Prolog, we can easily pass HTML documents into a list of such terms, strings and compound terms. And we are now not interested in the names of the tags, but in the number of tags. Of course, if we already have the names, then we can also simply count them. But let's do it from scratch. Let's define num tags, where we relate an HTML document, that is a list of such elements, to the number of tags. So, for example, in the empty list of elements, there are 0 tags. And if the first element is a string, that is a list of characters, and possibly remaining elements is, then the number of tags n is the number of tags in the remaining elements is. And finally, if the first element is an element term of the mentioned shape, that is name, attributes, and children, with possibly remaining elements is, then the number n of tags is the arithmetic sum of n1, the number of tags in the elements children, n2, the number of tags in the remaining elements is, plus 1 for the tag that's currently under consideration. So that's one way to define this relation. And there are other ways too. For instance, we could use 2 arguments for the number, where we have a relation between n0 and n. So like above, we are now in the situation that we speak about. We're describing here state transitions of the form n0, n1 and so on with the final state n. And we can think of this predicate as describing state differences, where in this case the state is an integer. For instance, the difference between n and n is 0. And here we're defining the difference between n0 and n, and here we're saying the difference between n0 and n is defined in terms of the difference between n1 and n2 and n2 and n. So we can interpret this as state differences and also as going from an initial state n0 to a final state n, where we count from 0 up to the number of tags. And the point is that DCGs let us express differences implicitly, not just list differences, but all kinds of differences. So whenever we encounter such a pattern, where arguments form a difference, we can simply remove the arguments and turn this into a grammar rule. Also here, n0 and n form a difference, so we remove these arguments, use a grammar rule, and also here, remove the arguments in the body. Same here. Remove the arguments, use a grammar rule, and for actual Prolog goals, we use a grammar body goal, like this. And we simply remove these arguments, okay? And we see here that only one of these rules takes the state into account explicitly, because only here, in the grammar body goal, do we see a relation between n0 and n1. Whereas the other rules simply thread the states through implicitly. And we can use semicontext notation to reason about the state difference, because now n0 and n1 are both singleton variables. They don't occur anywhere else in the clause. So let's define a non-terminal state with 2 arguments to reason about state differences within grammar rules. We say state holds for its arguments s0 and s if, and now we describe a sequence, and the sequence shall start with s0. So we use the terminal s0 to say the current state is s0. So in fact, we're describing a sequence with one element, namely the current state. And we use semicontext notation to express from now on, that is after this rule, the state is s. So procedurally speaking, we remove the current state s0 from the sequence, and we add the next state s to the sequence. So this is our definition. The current state is s0 and the next state is s. And by the way, we don't just count the number of tags, rather we describe the number of tags in an HTML document, because we can use the same program to generate a document and a number of tags. And we can also ask, does a document have a certain number of tags and so on? So we watch our wording and aim for declarative descriptions. Now, with this non-terminal, we can say n0 is the current state and n1 is the next state. So in our case, the state is simply an integer. So a major attraction here is that we need far fewer arguments because the state is now passed mostly implicitly. And only one of the rules needs to take the state into account explicitly. And now, if we again make a network connection to a website obtaining a stream S that we can read from, and use again load HTML to obtain a document object model from the stream, then we can ask for the number of tags in the DOM. And we use phrase with 3 arguments, so we specify 2 additional arguments. First, the list that consists only of the initial state, namely 0. So we start with 0 tags. And the remaining sequence is the list that consists only of the final state, namely n, the number of tags. And as answer, we get a substitution for n. So in this way, we can count the number of tags as a relation between states from n0 to n, using a DCG to describe the state differences implicitly. And as mentioned, we can do more than counting, because we can truly ask for the relation between n0 and n. So also the initial state is now a variable. And you'll notice that passing arguments implicitly like this is very similar to Haskell's monads. And we can also pass multiple arguments as a single term, simply as a compound term, such as S of arg1, arg2, and so on. And there's also extended DCG notation for this. And by using DCGs in this way, many imperative algorithms can be transcribed almost verbatim to Prolog. That's a major attraction of DCGs. For instance, let's take Tayan's strongly connected components algorithm. And here's an imperative formulation of the algorithm. So to implement this, we must maintain an index, a stack, we must perform assignments of variables, we must increment the index, we must push a vertex on the stack, and so on. So this is all formulated in imperative terms, where we modify variables destructively. For instance, after pushing a vertex on a stack, the previous state of the stack is simply no longer available for reasoning. And in Prolog, we don't have destructive modifications. So we need to express this all in terms of relations between things. For example, we can express pushing a vertex on the stack as a relation between 2 states of the stack. And also in Prolog, we don't have such global variables. So to implement this algorithm in Prolog, we have to pass around the stack, the index, and so on as arguments. And the good news is that DCG notation allows us to pass around the arguments implicitly. For example, here's a quite direct Prolog transcription of the algorithm. We use phrase to pass around the index, the stack, and the predicate defining what a successor is. And this is the initial state. And in these non-terminals, we only refer to the current vertex. The rest, like the stack, is implicit. Or for example, to increment the index, we don't need any argument at all, because the index is passed around entirely implicitly, like the stack. And if we actually want to refer to the current index, then we use our state non-terminal. In fact, we're using here a version of state that only uses 1 argument, so that we can reason about the current state. Whereas the version with 2 arguments lets us relate the current state to the next state. So for instance, to push a vertex onto the stack, we relate the current version of the stack, represented as a list, to another list, where the vertex is the first element. And it's also clear how we can implement state with 1 argument, by simply saying there's an element, the state in the sequence, and that element remains in the sequence. This is exactly like Lookahead. And this is the version of state that we've already seen. So this is how we can readily transcribe imperative algorithms to Prolog. And DCG notation helps us a lot to keep the code simple and readable and also easy to modify. And DCGs help us also in many other situations. Every time we want to conveniently describe sequences and lists. For instance, take Quicksort. This is a well-known and often very slow sorting algorithm. And it works by selecting a pivot element, and then it partitions the other elements into 2 groups. Those smaller than the pivot element and those greater than the pivot element. And these 2 groups of elements are sorted in the same way. And the pivot element is placed between the 2 results. So let's define the empty list sorted is the empty sequence. And a list with at least 1 element E and possibly further elements E's sorted means that we choose a pivot element and partition the remaining elements into two groups. So let's take, for example, the very first element, E, as the pivot element. And the remaining elements, E's, are partitioned into those smaller and those greater than E. So we assume that we have such a predicate. And the sequence we are describing is first the sorted smaller elements, then the pivot element, and then the sorted greater elements. And that's Quicksort in Prolog. For instance, if we ask for the sorted version of this string, then we get it. Like this, using Quicksort to sort the characters. Now, of course, one may say that's not the genuine Quicksort, because the actual Quicksort modifies the array in place. And yes, that's right, the actual Quicksort uses in-place modifications. On the other hand, is this still useful as an example of DCGs? And I think so. It shows how DCGs allow us to describe lists very elegantly and conveniently. And we've now seen many examples of this, starting from the observation that DCGs let us conveniently describe sequences. We've seen that they're in fact an extremely versatile mechanism. And we've seen various use cases, such as describing lists and common relations over lists, member, append, last element, reversal, and so on, reading from files by decoupling the declarative description from actual I/O, describing output using format underscore, phrase to stream, and so on, parsing, and as a subtask of parsing, tokenization, or more generally relating trees to lists, such as describing the tags of an HTML document and so on, and also passing arguments implicitly, similar to Haskell's monads. And I think it's fair to say that DCGs are one of the key attractions of Prolog, because they're so versatile and convenient. And that's not surprising, because after all, Prolog was designed for convenient text processing, and therefore this grammar mechanism plays a very prominent role in the language. Yet, and somewhat surprisingly, the full potential of DCGs is only now becoming apparent, with the most recent Prolog systems, especially Scryer, Tau, Trella, and Ichiban Prolog. The key innovations of these systems are that double quotes is set to chars by default already, so that we can write strings very readably. This is the case in all these systems. Some of these systems implement a very efficient internal representation of strings, in particular Scryer Prolog and Trella Prolog already have this, and one of these systems even supports mapping files to memory for direct processing with DCGs, namely Trella Prolog. And we of course hope that in the future, more Prolog systems will follow the example of these systems and also implement these features.